Good morning. It's the physics video lecture, Physics 105A video lecture 38. This is the penultimate video lecture, and we'll wrap things up, and on the last one it'll just all be review and what is to be on the final exam. But for now we still have a great topic to explore. We're talking about systems of point particles, systems of particles under Newton's law. And let's go ahead and just write out what we have already found, and then we'll complete the discussion. Yeah, so we had for a whole collection of these things with their respective positions, that's R1, R2, etc. We had the force on the ith particle, and we broke it down into external and internal forces. Actually, this is J. So the force on the ith particle, that's why this sum here, Ij. I names the ith particle, J is the rest of the other particles. System of n particles, J not equal to I. Good. And then we decided that if, we kind of go back and forth between just referring to that force or breaking it up into external and internal. But if F can be written as minus the gradient of a potential energy function involving all n of those particles, and this is F sub I, then we have to take the three derivatives referring to the ith particle there. So if we have such a thing, you'd love to number things, right? So if we have such a thing, then energy is conserved. So if star, then energy is conserved. And that is the sum of all of the individual kinetic energy terms plus this potential energy equals constant. Okay, so we showed that, and then we went on to the conservation of angular momentum. So I'm going to draw some attention to what we found there. I'll leave this up, point at it. So what we found was that if the net external force vanishes, we found that linear momentum is conserved. And this is what we had. We had d dt sum over mi/ri first derivative. Okay. Of course, that was the sum over all of these things here. The second derivative, take the derivative there, was equal to the net external force. And that net external force was just the sum of these. Now the interesting thing was that the sum of the double sum here vanished because of Newton's third law. You have Fij plus Fji for every pair, vanishes. So linear momentum, we have this. So if the net external force is equal to 0, F net external equals 0, then this total linear momentum P equals sum over is equal to a constant. So this plays a huge role in collision type of problems that we'll study next semester. But I just want to bring out the significance of this double sum vanishing. So as an example, instead of just colliding 2 point particles, let's imagine we're having a collision of some very complicated objects. A big steel frame, a spaceship or something. Suppose we're having that kind of a collision. I'm just drawing some cubes here. Okay, this is a big steel framed object. Right, they're headed on collision course. You know, we've learned in the past that the total momentum will be conserved. So before and after the collision, and if they're going at an angle, there will be a resultant and so forth. It'll just be the resultant vectors. But when we're explicitly reminding ourselves what happened here, what happened here with the double sum that sums up to 0, in terms of the actual collision, is that whole unimaginable amount of interactions during the crunching, twisting collision, all those interactions sum up to 0. You could think, well, that is just an infinitely difficult or impossible dynamics problem to keep track of every crunch and break and twist and so forth of this object. But in fact, they all just sum up to 0. So this double sum up to 0 is actually profoundly important. And so basically you have some objects that have internal structure colliding in one way or the other. All that internal structure, the forces involving it just sum up to 0. And you're just left with conservation of linear momentum. Good. I'm not going to write more than that, but I said my piece on that particular thing. We've all dealt with linear momentum before, but we probably weren't aware of all the complicated stuff that we just summed out of existence just because of Newton's third law. Okay, what we're going to do next is continue with this for a moment. I'll go ahead and erase this stuff here. We're going to introduce the center of mass. Center of mass really has a natural introduction in the context of this problem right here. I'll go ahead and use capital R for the center of mass. And we know that's, well, I'll just define it. We've seen this before, MI, or I divided by total mass. So it's the sum of all these moments divided by the total sum. And that's a position. Now here's what we're going to do. And let's go ahead and just, for the sake of, let's let capital M equal the sum of all those little masses, okay? Constituent masses. So M R second derivative. I'm just cross multiplying over and taking 2 derivatives. Ri second derivative equals F net external, right? We still have everything up on the board. This, which came from the sum of those. Or in words, let's go ahead and write this out. Just rewrite this. Give it a new number. F net external. Yeah, what does that mean? The total mass times the center of mass position. Total mass times the acceleration of the center of mass, which is a position in space, is equal to the net external force. So this is in fact what we always use when we take an extended object, say a tennis ball or a baseball or something, and we say we launch it and we identify the position with, of this extended object with one point in space, center of mass. So the center of mass moves as though the net force were concentrated at the center of mass. So total mass times this center of mass, and that's our justification for just associating, say, the position of the baseball is just the center of the baseball. Of course, let's go ahead and call this an example basic projectile. But it gets more interesting, say we throw a horseshoe. Okay, so there's a horseshoe. And where's the center of mass of the horseshoe? The center of mass is located somewhere here, I'll just guess. And if we throw a horseshoe, it's that location that's going to undergo projectile motion. So the net force is concentrated here at this point, at which there isn't even any material. So yeah, a lot of interesting stuff going on with the reduction of the system point particles to the simple equation again. And the same with more complicated objects. It gets interesting, say if you have some athletes who are jumping, diving, and what have you, and then their center of mass, once they're in the air, their center of mass is what's just undergoing projectile motion of some sort, even though they're twisting and turning, and so forth. Okay, I'll just put here athletics. Interesting examples there too. So now we have conservation of energy, conservation of linear momentum. And even though this was just 3 equations out of a semi-infinite number, see we got a really strong result out of that. We have one more important conservation law that's going to be angular momentum. So let's go ahead and have a look at that. We'll send this up here. No, we can actually erase here. So the angular momentum discussion is going to begin with the same equations of motion. So we've got our system of point particles, n point particles equals the external force on the ith particle plus the sum of those internal forces, Fij, j equals 1 to n, j not equal to I. So we start with that. This time, however, we cross multiply from the left, vector product, so now we're going to have m sub I, r sub I cross r sub I second derivative equals r sub I cross external f sub I, and then we're going to sum over this r sub I cross f sub I j of the internal forces, I equals 1 to n, I not equal to j. Right? If this is an equation, then so is this. And having done this step, we'll go ahead and do the summation again. So sum over I r sub I cross. Yep, lost the mass there. So m sub I r sub I cross r sub I. Two derivatives. Sum over r sub I cross. External force. And now the double sum. By the way, this was sum over j. J not equal to I. Right? You gotta be careful here. The the label was I, so that has to remain, and then we sum over j, and it's still labeled I. Okay, good. I and j. I not equal to j. R sub I cross Fij. Okay, put a box around this. Focus on it. Yeah, so you might be thinking that we have to bring this double sum to vanish again. And we will, and the conditions here, there are more stipulations than simply Newton's third law. So this is an interesting little step. So yeah, we'll write the double sum vanishes, and then we have to see why it vanishes. Not quite as simple. So we'll keep numbering here. Double sum vanishes. And we'll take these things pairwise again. So we're going to look at Ri cross Fij plus Rj cross Fji. And so if we take all of the mixed pairs here, or all of these pairs, Ij and Ji pairs, then that would cover the entire double sum. So what's going on here is, first of all, we have Fij equal to minus Fji. So we're making use of Newton's third law again. Newton 3. So if we do that, then we have Ri minus Rj times Fij. Oh, cross product, sorry. Cross product Fij, right? Because the Fji was just minus, Fij. So we've used Newton's third law, and the next assumption we're going to have to make in order for this to vanish is that Fji, the forces Fij are central forces. So it's good that we've studied the central force problem. They are central forces. So what we can do is we can write, and to be strictly speaking, how were we defining? So we had Fij was the force of the jth particle on the ith particle. Here's how I'm going to write this. Is equal to Ri minus Rj cross. Point I'm trying to make, and I could actually just state it. If these are central forces, then they're proportional. Yeah, I'll do it this way. Fij are central forces, so Fij is proportional to Ri minus Rj. It's enough to say that. I don't know what the sign is or what the actual law is. Okay. So let the argument have been made here. So these are central forces, so we know that's the defining characteristic, right? Proportional to the vector joining them. Recall we had F was equal to, in the central force one body problem, F was equal to F of R times the unit vector R over R, right? So that unit vector R over R is just proportional, this one. This unit vector would be this vector divided by its magnitude. So okay, that point has been made. Since they're central forces, and therefore, if F is proportional to that vector, then the cross product vanishes. Equals 0. So that's how we bring the double sum to vanish. We require that those forces between the point particles be central forces. Okay, so I'll come back to that. So what we now have is we brought this to vanish and we just have these terms here. So I can use this side of the board. And we'll call this 9. Yeah, now we're looking at this thing here. We have sum over, well, let's do this. Let's just look at the complete time derivative of the sum of m I r I cross r I first derivative. Okay, so the complete time derivative of that is just it's just a product rule. M I r I dot cross r I dot plus sum over m I r I cross r I two derivatives, right? We're just doing a product rule on this derivative of this one and then derivative of that one. And of course these are parallel, velocity crossed with itself. So this is 0. So that the left side of our equation here is given by the time derivative. So now we have complete time derivative of m I r I. And, I'm going to rewrite this now. R I cross m I r I dot, because we recognize cross product of the position and the linear momentum. So that's a good way to put it. Is equal to this thing right here, which we'll rewrite R sub I cross F sub I external. And this is the angular momentum. So directly underneath, I'm just going to write dl dt, the time derivative of the angular momentum, which is defined right here, is equal to the net external torque. So we'll write tau net external. Okay, so they're all defined right here, so go ahead and put in a little more if you need to. This is what we've found. And if there is no net external torque, then the angular momentum will be conserved. Here I'm going to consult the clock. Okay, great. We can just discuss this a bit more because this is what we wanted to arrive at. Okay, so let me send this up and talk about it a bit more. So I can keep numbering here. And if the net external torque vanishes, then angular momentum is conserved. Then total angular momentum is conserved. So no net external torque, total angular momentum is conserved. You know examples of things spinning around about their axis, that type of thing. Couple of points on this, and actually all three of them. The example we've already been through was our two-body problem that turned into the Kepler problem. We had conservation of energy, we had conservation of linear momentum, we had conservation of angular momentum. We, for the linear momentum, at the time we didn't explicitly talk about it. It was there in the sense that, we chose the center of mass as an origin. Okay. So let's finish this up with the conservation laws. Add a number, yeah, 11. Conservation laws and the two-body problem. You can barely read that. Two-body problem. So energy we had. Actually, how about we write the two-body problem up just explicitly and see what we had there. Remember, we had m1 r1 second derivative was equal to. I'm not going to run through that. I would actually be running through the whole problem once again. But I will draw the picture. That's better. So this was M1, I'll draw it big enough. This was M2. M1 and M2 both had their positions. Okay. And when we chose the center of mass, remember I drew that star there, and I had this vector. Let's leave the star for a moment. Remember when I defined the difference vector, R1 minus R2, we just called it R, and I expressed R1 and R2 in terms of R with respect to the center of mass. That's how we defined it. We were making use of the fact that center of mass, that point in space, is what's moving uniformly with constant velocity, and therefore we just shut out that whole motion. Okay? So we chose a center of mass coordinate system, where we based these coordinates on the center of mass. Yeah, and that is an expression of the conservation of linear momentum. So, center of mass, coordinate system, so that was your conservation of linear momentum. So that's the one we did first. Okay. So center of mass system, at my little star there. In this case, the star isn't an equation, it's that center of mass right there. So because linear momentum is conserved. So we didn't have to actually prove that at that time. It's intrinsic, it's part of the system of equations. Right? I proved it in general, but we were making use of that fact. Is conserved. Okay. And then the second thing we did was we used energy was conserved. Because we had U equals minus alpha R1 minus R2. That's why that worked. And remember, we had alpha over R, and that R was precisely that, okay? So if you can do that and get the forces, you have your conservation of energy. And angular momentum we did explicitly as well. So angular momentum, we defined L was R cross M R dot. But that actually was conserved because of the central force. So that explicitly went into the conservation of angular momentum. And then it showed us that motion is restricted to a plane. We did the plane polar coordinates, and then we were off and running. But yeah, we made use of all three of these situations, conservation laws, at the time. All right, here, etc. Here I'm referring to the calculations we did back when we were doing the central force problem. Okay, good. That's where we're going to leave it. That really ties things together. Our next hour will just be complete review, like I said before, and discussion of what's going to be on the final exam. See you guys then.